All right. Well, it's 1:30, so we're gonna go ahead and get started. Um, right off the bat, are there any burning immediate questions that you guys need answered or need to figure out how to answer? All right. Well, if there's no immediate questions, I'm gonna go ahead and start down with this towards machine learning section. Um, because it is the one section that wasn't covered on either of the. Actually, no, I think we can start here. I don't think this one was covered on the previous exam. But we're just gonna work our way from the most recent material to the older material because the newer stuff hasn't been covered yet. All right. So, for this question, we're trying to calculate the residual. Um, when the mother is like, we're gonna use this percentage of a certain grade for each major. Yeah, I will get that one in just a second. I'm gonna do this one real quick. So we're given this equation to find the daughter's height using the mother's height. So it's gonna be daughter is equal to 32.586 plus 0.626 times mother's height. And if we're given the mother is 58 inches, we're just going to plug that into the equation. So I'm just calculating it out right now. So we're expecting the daughter's height to be 68.894 inches tall. And the residual is just the difference between actual or expected minus actual, or actual minus expected. So if you had a graph and this was your prediction line, here's what we expect, and then here would be the actual. So it's going to be 67 minus a 68.894. So we get minus 1.894. Or I guess it's 11? Oh, right. Yeah, no, it's 57. I did 67 inches. Sorry about that. It's 57 minus a 68.894. I read it as 67. So the residual is going to be the 11. Percentage for of a certain grade for each major. Yeah, sure. Do you know which section that was in? Hannah? Was it this question right here with the percentage of B's given in every section? All right, yeah. So for this one, I'm just going to go ahead and get rid of that so I can do some coding. We need to figure out the percentage of B's in every section of every course at Illinois. So let's look at our columns that we're given. So we have the year, term, subject, number, and then the different grade types. So A plus all the way down to W. But we only care about B's. And then we also have count, which is the total number of students because that's the total number of grades. So we need to create a new column where it's just going to be the percentage of B's in that class. So the way we're going to do that is first you create the new column by doing the regular notation, and it's being called percent %B. And that's going to be equal to the df at B divided by the df at count. So what you're doing is you have a data frame, and it's all these columns are just integers, and then this is the total number of students. And percent %B is just the number of B's divided by the number of students. Does that make sense? And so if you had a different letter, so if it was the percent B minuses, you would just throw in a minus here, or a plus there, or B plus, or A, whatever you want. Okay, cool. All right, so I'm gonna head on back down to the machine learning questions. All right, so for this one, we're trying to find the y-intercept. Do you know like the question name so I can pull that one up on the screen? Because I can't really tell because it looks like it's copy and paste and it didn't copy and paste over right. Yeah, it should automatically get uploaded to YouTube after. It'll probably be in like the live tab on the Discovery Channel. Alright, while we try and get that one question figured out in the chat, I'm not sure which question that is. Regression on mother-daughter heights. Okay, let's see if I have it. Is it asking for the is it this question right here? Except instead of asking for the residual, it's asking for something else. Is it this one right here? Where you're trying to predict the daughter's height? Okay, so for this one, we need to calculate our slope because it's not giving us the slope. Because we know that the linear regression is going to be giving us the form y equals mx plus b, where y is the daughter's height, m is our slope, x is the x value, or in this case, it's going to be the mother's height plus our y-intercept. So we're going to have to calculate our slope and our y-intercept. So the slope is going to follow the equation of r, so our correlation coefficient, times sdy over sdx. So that's how we calculate slope in this question, I believe. It's been a minute since I've done this, but from what I remember from office hours, it's this. So we have our r is 0.57, so we're just going to plug that in. Our standard deviation of y is 2.8. And then our standard deviation of x is 3.3. And you know it's 2.8 and 3.3 because the daughter's height is 2.8, and we're trying to predict the daughter's height. So that's our dependent variable, that's our y variable. And then the same thing with the mother's height, that's our independent variable. So that's going to be our x value. So plugging that in, we get a slope of 0.4836 and a bunch of 3/6s, but that's probably fine for now. And then, so now we have daughter's height is equal to 0.4836 times the mother's height plus our y-intercept. But since we don't have our y-intercept, we're going to have to calculate that, and we're going to use that by using our averages. So it's going to be 70. We're plugging in our average daughter height is equal to 0.4836 times our average mother height of 64 plus b. And then we just need to solve for b. So 0.4836 times 64 gives us 30.9504. And we just have to do 70 minus that to get 39.0496 is our b value. So now we have our equation of daughter's height is equal to 0.4836 times the mother's height plus 39.0496. So now we have a mother who's 53 inches tall. We just got to plug that in here to solve for our daughter's height. So let's go ahead and plug that in. Times 53 plus 39.046. Let me do this real quick. And then, so we plug that in and we get 64.6768 for our daughter height. And now hopefully I did everything right. And then we get our daughter's height. So this is a kind of difficult question. It's a multi-step process. First, you want to calculate your slope, which is shown in this step. Step 2, we need to calculate. So this is still the slope calculation. Step 2 is to calculate our y-intercept, which we use by using our averages to get our y-intercept of this. Step 3 is, now that we have our slope and our y-intercept, we can plug that into our model equation of y equals mx plus b, and then plug in the mother's height to get our daughter's height. Any follow-up questions on that one? It is very complicated. Typically you don't want to round till the end. That's just because, like, if you rounded early, because if you were to, like, in just a typical example, if you were to round 0.33333, a bunch of threes repeating, and then you add them together, you get 1, because that's 1/3 plus 1/3 plus 1/3. But if you rounded early, you would get 0.3 plus 0.3 plus 0.3, which is equal to 0.9. So that's typically why you want to use as many decimal places as possible until the very end of your calculations. At least that's my personal logic, and like, I'm sure, like, if I were to I'm gonna round the y-intercept here to just 39, and I'm gonna tell you, like, the so instead of it being 64.6768, which is the right answer in this case, it would be 64.6308, and that is 0.04 off, and I don't think that would, so it would be 6308. So if I plug that in, I mean, I guess it still works, but you typically don't want to round till the end. How many questions are on the final overall? Good question. Let me bring back up the practice exam that I was working on. About 65 questions, so it's going to be, yeah, so if you click on a question, it'll say make sure your answer contains at least 3 decimal places. But how many questions on the final? 65, and it's exam 1, and then exam 2, and then the stuff you've learned since exam 2. So that's like it's essentially 3 exams stacked on top of each other. So it's about 65 questions, but you do have more than enough time to complete it. You get 3 hours in the CBTF. All right, so I'm gonna work on this one until I get another question. So now we have our correlation coefficient is 0.8, and we need to calculate our y-intercept. So this is essentially what I just did, but we got to calculate our slope. So slope is equal to r times s dy over s dx, but in this case they're equal to each other. They're both 14, so it's just going to be 0.8 times 14 over 14, so our slope is 0.8. Yeah, can you type in what it says right here so I can find that question at the top? Like here it says question 57, regression on course exam grades. Can you type what it says after the question number? So we get our slope is 0.8, and then we just have to do the same thing here. So we have to do our average y is equal to 0.8 times our average x of 74 plus b, and then now we just solve for b. So 0.8 times 74 is 59.2, 82 minus that is equal to 22.8, and that's our y-intercept. NBA salary confidence interval. Okay. Let me just check to make sure I don't have that one on here. I haven't looked at the confidence interval questions yet. Sugar intake. Oh, this one. Okay, cool. So, the sample mean salary of 500 NBA player is $4 million. The population standard deviation for NBA players. So our population is all NBA players ever. Our sample is these 500. So we know that our X bar, our sample mean, is equal to 4. And this is represented in millions of dollars. So, and our population standard deviation, so sigma, is equal to $0.8 million, which is also 800,000, but it's in millions of dollars, so we can just use the numbers they give us. And for a confidence interval, our formula for our confidence interval is X bar plus or minus our confidence level Z value. So it's a Z score of 90% confidence times our standard error. So let's go ahead and first calculate our standard error, which is going to be standard deviation over root n. So that's taking our population and standardizing it to our so it's taking our population and standardizing it to our sample. So we have 0.8 over root 500 to get 0.035777. So that's what I'm going to be using. Our X bar is 4. And then I'm just going to Google it, and then I'll show you how to get this. So our Z score for 90% is 1.65, and then let's verify that. by going to our Jupyter work book that's given to us on the exam. Alright, now that it's open, we are gonna from scipy.stats import norm, which you guys should have done before, and then we're gonna do norm.ppf of point, is it 0.95? Yeah, it's 0.95. So the way you get that 0.95 instead of 0.90 is you do 1 minus your confidence level, so 0.9. Divide that by 2, which is where you get that 0.05 from, and then you slap that onto your 0.9. It's kind of a weird thing to think about, but for that's why it's going to be 0.95. So now that we have that, I just got to find the question again. All right, so it was 1.65 times 0.035777, and it wants our rightmost, the maximum value of our confidence interval. So all we have to do is just do 4 plus 1.65 times 0.035777, or times the standard error we calculated. I'm just going to use the whole number on my calculator here. And it's going to be 4.059. That's our right side. And I'm going to calculate the left side just for fun, because if it asks you, you're just going to do a minus instead. That's going to be 3.941. So that's our confidence interval. So if it asks you for the minimum, you'll give the left side. If it asks you for the maximum, you'll give the right side. And if it asks you for the range, you will give the right side minus the left side. So it's 4.059. Okay, margin of error for GPA. Let's see if I have that one. Oh, right here. I'm going to leave this calculation up for just another minute. So I'm going to leave this one up just for another minute here. Okay, so now we're going to start on this one. So we have a 90% confidence interval with a margin of error of plus or minus 0.0164. So what the margin of error is this calculation right here. So we know that from the last question for 90% confidence interval, our z value here we're using is the 1.65, and then our times our standard error is equal to 0.0164. So we have to find what the standard deviation is for this. So let's, instead of representing this as standard error, let's represent it in terms of standard deviation. So it's going to be standard deviation over the square root of n. And in this case, our n is 1600. All right, so let's go ahead and simplify this. So we get 1.65 times our standard deviation, and then over our square root of 1600, which is just 400, I think. Or 40, sorry. Over 40 is equal to 0.0164. So let's multiply the 0.164 times our 40 to get 1.65 times the standard deviation is equal to 0.656. and then divide that by 1.65. And that gives us standard deviation is equal to 0.397575. 0.397575. So that's how we go ahead and do that question. Okay, so that was the MBA salary and margin of error back to back. I think the final is weighted 200 points because the course has 1,000 points and it's 20% of your grade. So it would be 200 points on the finals gonna be weighted 200 points, and your previous exams are weighted 100 each. I can check to see if I have the candy problem on here, but it looks like you got a video of that. Do we have any other immediate questions, or do you want me to just keep answering some of these newer material stuff? All right, I'm going to head on back to the towards. All right, so this question is kind of annoying to do sometimes when you do it by hand. So what I would recommend doing for this question is to not do it by hand, but instead to use code, which you all know how to do. So we're going to import pandas as PD. All right, and then the first thing we have to do is we want to make a data frame. And we're making a data frame of these two columns. So first let's make our list. So x is equal to 1, 3, 5, 8, 10, 11, 1, 3, 5, 8, 10, 11. Y is equal to negative 10, negative 8, negative 12. Negative 12, and I think it's just 3 negative 13s to round that out. Yep. Okay. And then we'll do df is equal to pd dot data frame of x. If I print out df, it's just gonna be that. So now we'll create a y column and set it equal to our y variable. And then if I print out df now, we get 0 and we get our x column and our y column, and we can just do df.core, which we've done before. So they have a correlation of minus 0.82325. Minus 0.82325. And that's the easiest question, or easiest way to do this question. The other way, doing it by hand, does take a while. All right, do we have any burning questions? Because if not, I'm going to move on to the clustering in the FIFA dataset. All right, so we have 3 positions we want. We want central attacking midfielder, a right back, and a goalkeeper. So FIFA 19, I think is the name of FIFA 19 at FIFA 19 dot. Sorry, it's gonna be double. FIFA 19 dot position is equal to CAM. Or, and then we're going to do this 2 more times, but with 2 different positions. and then it's RB and GK. So RB, GK. And then we also need where their overall rating is at least 70. So it's going to be FIFA 19 dot overall is greater than or equal to 70. All right, and we want 3 clusters. And it's just going to be k-means dot fit. And then it's going to be our 3 variables that we want. So short passing, long passing, and acceleration. Yes, we can do that one. I think it's this, but I might have the syntax wrong. Alright, what did I do wrong? Oh yeah, so it's, I misspelled acceleration. And then there's our 10 out of 10. So we need to do estimating RMSE. Okay. So estimating RMSE. So we are given the correlation coefficient R is equal to 0.04 and SDY is equal to 1.4. And then there's a formula for RMSE. It is RMSE is equal to R times square root 1 minus SD. Wait, I might have that backward. Let me just double check here. Yeah, sorry. It is SDY times the square root of 1 minus R squared. So RMSE in this case is our SDY, which is 1.4, times the square root of 1 minus R squared, and R squared is, R is 0.04, so R squared is 0.0016, 1 minus that, so we get RMSE is equal to 1.4 times the square root of 0.9984. So 1.4 square root 0.99 is equal to 1.39887. That's how you do that one. So RMSE is the root mean square deviation. So it's just it's essentially the distance. It's kind of similar to residuals. It's the difference between actual and expected, but in a different way. So it's kind of, I don't know if it's more accurate is the right word, but it's just like if I were to pull this up right here, we would it's just kind of similar to the residuals in this case. It's a kind of a complicated concept, but Yeah, so RMSE, like Angela's saying, average between the predicted and actual. All right, I'm going to keep on going with this stuff. All right, we're doing multiple linear regression on movies here. All right, so first thing we want to do is model is equal to linear regression. And then we need to do our model.fit. So model is equal to model.fit. And then we just need to pick our three categories. So production costs, and promotional costs. And then we are using that to predict, in this case, the receipts is the dependent variable. So, and then in the receipts, or in the predicted column, we just store in this line of code. And I have a typo or something. Oh. Extra space bar from copying. Alright, cool. Any questions on how you do the linear regression code? It should have been in the homeworks recently, so I think you guys know this one though. Alright. So, sample linear regression construction. Alright. So we have our R value is 0.66. And we're trying to predict score using the number of hours. So amount of hours spent studying and the score out of 100. So first, score is going to be equal to beta 0 plus beta 0 hat plus beta 1 hat hours, because that's just the form of linear regression. So now we have to calculate our beta 1 hat, which is R times SDY over SDX, because this is equivalent to the slope. Also for this question, little trick, we know the slope is beta 1 hat in this part because it gives us, so it tells us the slope is beta 1 and then the intercept is beta 0. So if you get confused, but you know which is your dependent, which is your independent, this will tell you which one is the slope and which one is not the slope. Or which one's the intercept. So we can just plug and chug. We get 0.66 as our R. Our SDY is 5.81. Our SDX is 2.38. 0.66 times 5.81 divided by 2.38 is 1.611176. So I'll just throw in 3 decimal places. And then intercept, which we've calculated before, we plug in our averages. So 70.68 is equal to 1.611176 times 6.4 hours plus B, and then we just gotta solve for B. Minus, so solving for B, I got 60.36847 is equal to B, so 60.368. Oh, sorry, the iPad was not showing because it wasn't pinned. Should be pinned now. So yeah, I'll go over that real quickly again. So the first step was calculating what our beta 1 was. I guess. So we got that as our beta 1. So it's R times SDY over SDX. So that's step 1. Plugging that in. We got our thing as that. So this is our slope right here. So yeah, the important part is the formula for slope is R times the standard deviation of Y over the standard deviation of X. So that's how we calculate slope. And then for calculating the intercept, you plug in these averages given to you for your Y and X. So this was given to us and this was given to us. We calculated this in our step 2, and then we just solve for B. Any questions on that? I know the work wasn't showing, so I'm willing to go step by step again. All right, well, if there's no questions, I'm going to go on to the next one. I'm willing to circle back, though. Oh, yeah, so we did just do this RMSE one, but I'll do it again. So RMSE is equal to SDY times the square root of 1 minus R squared. Ooh, okay. I will see if I have that one. So SDY is given to us as 1.2. R is given to us as 0.49, so 0.49 squared is 0.2401, so 1 minus 0.2401. I'm going to plug that into the calculator, so 1.2 times the square root of 1 minus 0.2401. I get a RMSE of 1.046. 1.046. There we go. Estimating Game of Thrones and handedness. Was it on the practice exam for this one? If so, what section was it in? Because I'll go ahead and scroll on down. I got the 70.68 from the average. I got the 6.4 from the average. So these two are given to us in the context of the question. Prediction and probability section. Okay. Let's see if I have it. Game of Thrones. Game of Thrones. This one. Yay, Game of Thrones. Love Game of Thrones. All right. So below is a survey about student handedness and whether or not they watch Game of Thrones. If we randomly select a student, what is the chance that they are not right-handed, given that they watch Game of Thrones? So for this question, it's asking, given that they watch Game of Thrones, so we need to think, we don't really care about these students in this question. I'm sure we care about them in real life. And we also don't care about the totals columns, or this bottom totals column, because we only care about this one. So we're only selecting from the students who watch Game of Thrones. And so the probability that they're not right-handed is you just take the 34 plus 15 to get 49. And then you just divide that by 340 because that's the total number of students who watch Game of Thrones. And you get 0.144. And then to double check the work, we can do 291 over 340. That's the number of students who watch Game of Thrones. And then just do 1 minus that. And we also get the 1.44. Or 0.144, sorry. Do you want me to do another variant of this one? Or does this make sense, Vicky? Or Victoria? Or whoever... yeah. I didn't do any work for this one. So when it says given, you only care about the column or row that is given. So no, it's still randomly selected. But when you randomly select a student, there's a probability. So we're trying to calculate the probability that of a random student that they're not right-handed given they watch Game of Thrones. So if it said randomly select a student, if you randomly select a student, what is the chance that they don't watch Game of Thrones given that they're ambidextrous? No, so it's not out of 662 because the 662 incorporates the students who don't watch Game of Thrones. So when it says given, it means that's the column or row that you care about. So if it was flipped, if it said what is the chance that they don't watch Game of Thrones given that they're ambidextrous, well, we only care about the ambidextrous students, so we know our denominator is going to be out of 29, and our numerator is going to be 14 because those are the ambidextrous students who don't watch Game of Thrones. So the reason you don't use the 662 is because of the given. This is more marginal and not, or conditional and not like overall. We don't care about the students who don't watch Game of Thrones because it's given that they do. Let's see if I have that candy question because I love to answer the candy question. It's like my favorite question. Okay, I don't think I have the candy question on here. I can answer it later if it needs to be answered. But I'm going to go back here. Pairs of variables. Oh, yeah, this one that we're on right now. Perfect timing. So for this case, it's asking for height in inches and height in centimeters. Well, it's both height. The only thing that differs is the units. So we know that they're going to be directly correlated because they're the same variables. Because if you had 1, 2, 3, 4, 5, 6, and then you essentially manipulated all those rows to be times 2, you'd have 2, 4, 6, 8, 10, 12. Well, the correlation between them is going to be exactly 1. Yeah. So it wouldn't be over the 662 because we already incorporated the fact that we only care about the Game of Thrones watchers. But yeah, so it's going to be exactly 1 because these two are just the same. One of them is just a manipulation of the other. So if the data is manipulated, if the data is the same data just manipulated somehow, whether it's multiplied by a factor or whatever, it's gonna pretty much be the same. But if for this pairs of variables question, hours of sleep before a math exam and an exam score on a math exam, it wouldn't be exactly 1 because the hours of sleep and the score aren't the same. What if it is for different units instead of both being height? So like this one right here. I think there's a slight delay on my end. Because if it's not this one, I'll pull up another variant. Do you have a specific question in mind? So all right. So this one works. Okay. So hours. So for this, okay, it's this one. So we know, or like we've seen studies where when you sleep more, you tend to get a higher exam score, right? Like if you had a low amount of sleep, you're tired, you're exhausted on the exam, you're probably not going to do as well. If you're well rested, you're going to probably do better because you're able to think more, right? You know, you're kind of clear headed. So in this case, they're not directly related because they're not a manipulation of one another. And in this case, we know that more hours is going to lead to a higher score. So we know it's going to be close to 1. We know it's going to be positive. If it was more hours leads to a lower score, I don't know, like more hours playing video games is going to lead to a lower score. It would be closer to -1, but because it's to a higher score, so like right here, if I have this graph and this is hours sleep the night before and score, as you know, if we have we expect students who had low hours of sleep, like right around here, and then as you know, as their hours of sleep increases, we're expecting to see more scores in this area. So our line's gonna look like this. You know, you draw a line through it, it's gonna be positive. So it's gonna be between 0 and 1. But if it was hours gaming, ignore the handwriting, and score on an exam, the more hours spent gaming, the lower score we expect. The less hours spent gaming, the higher score we expect. So it's going to be between 0 and -1. I don't think it'll trick you. I think it's just kind of, they want you to take your time and think it through. So when I say units are related, I mean height and height. Like the exact same. You know, if I did over here, number of classes skipped and GPA would be related. We know that these two aren't the same variable, and we know that as you skip more classes, your GPA is lower, so we know it's going to be like this. Like this one, it's number of points scored on exam 1 and number of points missed on exam 1. I actually don't know. This one might be a trick. Yeah, no, it's not just -1 because for, you know, when you answer a question, you either got it wrong or you got it right. And so the number of points scored and the number of points missed, they're a manipulation of each other. You know, so if like that one, it was hours spent doing homework, hours spent watching YouTube. Sure, they're both hours spent, but they're not hours spent doing like, well, I guess they would kind of be related a little bit. But like shoe size and ACT, no correlation, no relation whatsoever. It's people with higher shoe sizes don't get higher scores. We don't know that. We can't prove that. And like this one, we already answered. It's between 1 and 0. You know, this one is gonna. This one's gonna be -1, right? Because it's when you think about it, it's between 0 and -1, isn't it? It's because the hours you spend watching YouTube takes away from the hours you spend doing your homework and vice versa. So it's gonna be between 0 and -1. So it's not trying to trick you, because if this was like hours spent doing homework and hours spent doing stuff that isn't homework, not just YouTube, it's probably gonna be -1 just because those two things are like directly related. But if you're not doing homework, you're also, you know, there's other stuff you could be doing. So just kind of the way you think about it, you just gotta kind of think it through. All right, so this question we've done a bunch today. I'm still gonna go through it. We've not done it a bunch. We've seen it a bunch of different ways. So we have our R is equal to 0.9. We need to calculate the slope. We know the slope is R times SDY over SDX. Okay? Yeah, it's just think it through, do the practice exam multiple times. You'll see every variation of that question. Yeah. Alright, so find the slope of the regression line predicting the first year box office earnings. So this is our y. Box office earnings are our y. Production costs are our x. So it's going to be 0.9 times SDY 32.7 over 2.3. 0.9 times 32.7 divided by 2.3. Our slope, we calculate it to be 12.79565,217. So 12.796. That's 23. 12.796. Our y-intercept, we know it's just going to be our averages, so it's going to be y bar is equal to 12.796 x bar plus b. We're given y bar and x bar. It's our average y and our average x. And we solve for b. So 83 is equal to 12.79. You can't read that. 7. Wow, my handwriting is bad. 796 times our 8.8 plus b. Solve for b. So times 8.8. And I might have done something wrong, but I don't think I did. Let me just double check. I did, wait. No, I didn't. Okay. So we get minus 29.602. So this one, we've done it a bunch today. Memorize this formula. Memorize this formula. Oh, was it the one teacher question? Teacher salaries question? Because if it's a teacher salaries question, they did remove that question, the one with all the errors. It was posted in Discord. Confidence intervals. Do you remember what question it was, like, exactly? But if it's a confidence intervals question, confidence interval changes. Okay. Oh, yeah, yeah. Fun one. Okay. This question, right? Alright, so for this one, it's our confidence interval for 95% is going to be our x bar plus or minus 1.96 times standard deviation over root n. And in this case, our n is 1,000. So root n is a weird number. I'm just going to type in root 1,000. Right? And when we increase our standard deviation, so if our standard deviation for this one was 2, or let's do 5. If our standard deviation for this one was 5, 1.96 times 5 over the square root of 1,000, we get a margin of error of plus or minus 0.30990321007. Long number, I know. And then we can do 53 plus or minus that, so it's going to be 53.3099, and then 53 minus that to get 52.690. It's 0, 1. So there's it for a standard deviation of 5. So when the second identical experiment was done, same number of children, they found a larger standard deviation. So let's just do standard deviation is equal to 7 for our second one. So I'm going to replace the 5 with the 7 and do the exact same calculations. We get a margin of error. So for standard deviation is equal to 7, we get a margin of error of plus or minus 0.433864495. And we do 53 plus that. Plus or minus that. So now, we get 52.566 and 53.434. So our right end is higher than our right end over here, and our left end is lower than our left end over here. So if whenever you find a larger standard deviation, the size of the confidence interval will grow larger. If you had a smaller standard deviation, it would grow smaller. Where did the 1.96 come from? That is the confidence level of a 95% confidence interval. There. 95% CI. I'm just going to try and pull up the formula on Google. It's just the z-score for 95%, so 1.96. If you did norm.ppf of 975, it's just norm.ppf of the value you need to get the 1.96. It's just yeah, so it's the ppf. So for a 95% confidence interval, you need you need 95% of the data to be, you're predicting that 95, you're saying with 95% confidence that the true mean is going to be within 2 ranges, right? So it's just the value that gives you the 95% confidence. So like in hypothesis testing, you learn about the alpha value, like you reject it if it's lower than 0.05. The 0.95 is the opposite of that. So if you did a confidence interval of 0.95, it would return the same results as a hypothesis test with alpha is equal to 0.05. Okay, Harshi did have a question. Average GPA of all majors. Average GPA of all majors. Oh wait, that one's not going to be on the exam, I don't think. Because it wasn't on exam 1. I think the only hard question from that homework is going to be the admission rate question. Because I think they removed the average GPA question. All right. I'm going to go ahead on to the polling and confidence intervals. All right, so student organization sampled students and claimed that the students' average hours of sleep per night at UIUC is 6.5 hours. Another RSO believes that the sample was not representative. They think it should be higher than Um, to investigate this, they randomly selected 50 students from various standings, graduate, undergraduate, law school, med school, whatever, and recorded their hours of sleep per night. The sample has a mean of 6 hours and a standard deviation of 2.2 hours. Conduct a one sample z-test with the above information and compute the test statistic and p-value. So we are trying to calculate that the probability that x bar is greater than 6.5. X, which is going to be equal to minus 6.5 over, I think it's over standard deviation over root n. So over standard error. So in this case, our standard, or our x bar is equal to 6, so 6 minus 6.5, and our standard error is standard deviation over root n is equal to 2.2 over root 50. Is 3.35355. So 6 minus 6.5 divided by that. That's going to give us a z-score, very large one. So it's the probability that z is equal to or minus 12.38477, which comes from doing this calculation right here. And then we can just do norm.cbf of, that's going to give us the area to the left, but since we're doing greater than, we do 1 minus to give us the area to the right, and it's a very low number. So I think I did something wrong, but it's going to be this one. We know it's going to be a negative z-score. I calculated something wrong. I don't know. Wait, is it just... Okay, well, our z-value was wrong, but it's plot 3. The way I knew it was plot 3 is 6 minus 6.5 is a negative number, so we know our z is going to be negative. We're not doing a two-sided, so it's not going to be this one or this one. And then we're doing greater than, so it's not this one, so it's going to be plot 3. We didn't really need to do any of the math. All right. So this is going to be FIFA 19 at FIFA 19 dot position 1 hypothesis testing. No, we're getting the hypothesis testing soon. I will actually just come back to this one later. Winning roulette. Not that. Not that. Or I guess, do you have a specific question in mind, or do you want me to just do one of these ones? That I can find. Like, do you have a specific one that you struggled with on the practice exam? Anything works. Is it one of the ones where it's like the fill in the blank questions, or is it just one of the ones where you do everything on your own? Like, is that what kind of question are you looking for? One of the fill in the blank ones. All right, let me see if I can find. Is this Aaron Rodgers one good enough? Daily sugar intake. Yeah, I can do the daily sugar intake question. I think it's this one. Oh, question 45. So this 18 reds, 18 blacks, 2 greens. So for this one, we're going red every single time. So we only win when it hits red. So the probability that we win on a red is going to be 18 over, I think it's 38. So the probability of winning on red is 18 over 38. The Aaron Rodgers one or the roulette one for the person who's asking. And then for the question where we're supposed to find the p-value and t statistic, can you pull up the exact instance you're looking for? That way I can find it on the practice exam a little easier. I can just search like the name of it and then find it. All right, I'm gonna finish this one. So the probability of winning on red is 18 over 38. Yes, we can still go over the candy problem. So the probability of winning when you only bet red your probability of winning on a given time is 0.4736842105. Okay, and we're playing it 130 times. Okay, fill in the blank one. Why? It's 38, not 32. I got distracted. How often is the bus late? Sure, yeah, I can do that one too. So how often is the? Sorry. So it's 38 because there's 18 reds, 18 blacks, and 2 greens. 18 plus 18 is 36. 2 plus 2 is 38. So that's where we get the 38 from. We get the 18 because we're only betting on the reds. So 18 over 38. This is our probability of winning. All right. And so we play 130 times in a row and count how many times we win. What is the expected value of the number of wins? Well, expected value is equal to n times p. So it's equal to 130 times our point 47, 36, So when we play it 100 times in a row, or 130 times in a row, 57, 8, 9. That's it. Okay. So the Aaron Rodgers question. I'm gonna do Aaron Rodgers, bust late, candy. All right. So Tom, Green Bay Packers fan, and Aaron Rodgers fan. Aaron Rodgers is a Jet now, so that's great. We love that. He claims that Aaron Rodgers' average number of touchdowns per game is 2.29. Dave, a hardcore Bears fan, believes that Tom might be inflating Rodgers' statistics. So from his debut, which was in like the very early 2000s, until 2019, Aaron Rodgers played 175 games. Dave doesn't want to look at all of them. Dave's the Bears fan. So he randomly selects 61 games. So N is 61. And finds a sample average number of touchdowns to be 2.1155. 2115. So our X bar is equal to 2.115. and our sample standard deviation is 1.343. So we're trying to say that Dave is trying to prove that Aaron Rodgers throws less than 2.29 touchdowns per game. So it's going to be a one-sided test because we think it's less than, and it's one sample because we're only using Aaron Rodgers statistics. All right? So we kind of answered this with part one, but it's mean. The true mean is 2.29. Our alternative hypothesis is that it's less than 2.29. Test statistic is equal to x bar minus mu over standard deviation over root n. So it's 2.115 minus 2.29 divided by our 1.343 over root 61. So I'm going to plug that into my calculator, and I'm going to get 2.115 minus 2.29 over 1.343 divided by square root of 61. So I'm getting a test statistic of minus 1.0177. I'm going to check it on this calculator. So numerator is 2.115 minus 2.29. Our denominator is equal to 1.343 divided by 61 to the 0.5. And then we're just going to do our numerator divided by our denominator, and we get the same thing that I just calculated. Or over here. And then we need to compute the p-value, so the probability that z is less than that. So that's our norm.cdf of that, the value we just calculated. And we get a p-value of 0.15. And since we get a p-value of 0.15, which is greater than our significance level alpha of 0.05, we fail to reject the claim. So we know it's not C or D, and then let's take a look. So we can't conclude that it's equal to our sample statistic. So there is no evidence to support Dave's claim that Aaron Rodgers throws less than 2.29 touchdowns per game. So that's how you go ahead and do the Aaron Rodgers question. Aaron Rodgers, so does that make sense for the person who had the Aaron Rodgers question? Alright, so I think that you guys are good on that one. And then how often is the bus late? Okay. So now we're going to do the bus question. MTD claims that at Dave's bus stop, Bears fan Dave, the bus is late 12% of the time. Dave believes the true percentage to be higher than that. So in a sample size of 46, the bus was late exactly 10 times. So first, it's a one-sided one-sample z-test because we think it's greater than the number and we're only using one sample. So again, our true mean is what's given to us by MTD. So that's our null hypothesis. So we know, or it's not mean, it's proportions because it's percentages, sorry. So our null is that it's equal to 12%. Our alternative is that it's greater than 12%. And so the way we calculate our test statistic for proportions is Z is our test statistic number, is equal to P hat, so our sample, minus our true P, divided by our standard error. But because it's a proportion, our standard error takes on a different form. Our standard error takes on the form of P times 1 minus P over N. And then you square root that. I don't know if I already said that, but you square root it. So that's how you calculate the Z, our sample proportion. I'm going to see if I can make this a little bigger so you can see the writing. All right, so let's plug in all of what we know. So we know that P is 12. But in this case, it's a proportion, so it's going to be 0.22 or 0.12. So square root 0.12 times 1 minus 0.12 over, and then our N is 46, given to us in the problem. Let's go ahead and solve that. Square root times 46. So we're getting a Z value of 0.047912. 9646. That's our standard error. So that's going to go here. And then our P hat, we need to calculate that. That is 10 over 46. So 10 over 46 is 0.217. But we're just going to keep it as 10 over 46. So 10 over 46 minus our true P of 0.12 divided by our standard error that we just calculated. I don't want to rewrite it, so I'm just drawing the arrows. So if I'm plugging it into my calculator right now. So 0.12 divided by 0.0479129646. So I got a Z value of 2.0326712223. I'm going to show you guys how to do that. Why is it 1 minus 0.12? So, 0.12, because the formula for standard error is P times 1 minus, square root of P times 1 minus P over N. Yes, we can do the SpongeBob question. So I'm going to finish this one, find the candy problem, and then do the SpongeBob question. Alright, so we got our Z. I'm going to redo that calculation here. So first, let's calculate our standard error. So it's going to be equal to 0.12 times 1 minus 0.12. So P times 1 minus P divided by 46, because that's our sample. And then we're going to just check our work, 0.0479, that looks right. And then now we have to get our numerator is equal to 10 divided by 46 minus 0.12. And we get 0.097. So now if we just do that, we get our 2.036 that we, or 2.0326 that we just had. So there's that. And then our p-value, we're doing greater than, so we can do CDF gives you to the left, we need to the right, so we'll do 1 minus norm.cdf of our p, or of our z-score, and we get 0.02. Is it less than our alpha? Our alpha was given to us as, hang on, I need to make this a little smaller. .05, so it's smaller, so we reject the claim. So it's not C or D because we're rejecting, and there is evidence, so we can go with A. That's how you do the bus question. Any questions on the bus question? Okay, the book says because use 1 minus p. So the standard error formula is when you're doing a hypothesis test of proportions, which this is, it's the square root of the. When you do a hypothesis test, you do have to have your population mean. So, or what's given to you as a population mean. We're trying to prove that it is or that it isn't the population mean. So we're given a population mean of 12%, so 0.12. And we need to normalize or standardize that so we can then use the normal curve to calculate our p-value. So the way we do that is by doing p hat, so our sample minus the population divided by the standard error, because the standard error takes a standard deviation. Because the standard deviation for a proportion is p times 1 minus p. But when you have a sample and you're trying to get it down to the sample, you have to use the standard error, which is going to be, or it's square root p 1 minus p. But you have to do the standard deviation over it. So that's how you, that's how we got the p 1 minus p, because the standard deviation of a proportion is square root p 1 minus p. And so the 12% is the proportion that the bus is late. So there's like a 12% chance that the bus is going to be late. And we found using Dave's study that it's late 10 over every 46 times. So that's why we use p hat up here, as we're trying to compare it. So what the p-value is saying, what our p-value of 0.02 is saying, is that there's a 2% chance given that the population data says that the buses are late 12% of the time, there's a 2% chance that we find a sample of size 46 that is late. 10 over 46 is 22%. So there's a 2% chance that we find in a sample size of 46 that the bus is late 22% of the time. So that's what the p-value is saying, and that's like p is what's given to us, p hat is what we find, and then the standard error is kind of merging the two. All right, it's kind of a complicated concept to grasp, but it's just it's formulas. That's just kind of like formulas. All right, so time for candy party. So this one's a very fun question. So we have 2, 2, 4. That's a SpongeBob question, right? Alright, so apologies for my bad handwriting, but we have 2, 2, 4, 5, 5, 5, 8, 8, 9. 2, 2, 4, 5, 5, 5, 8, 8, 9. Alright, so first we're going to start by finding what our current median is. Current median is 5 because there's 4 to the right and 4 to the left. We have 4 candies remaining, and we want to create the highest possible median value. So we want to keep this number in the center as high as possible. But the issue is when you increase the number in the center, if it grows greater than the number to the right, then it goes to the right of the number to the right. So that sounds confusing, but like if I added 1 candy to our person with the median, so this person with the 5, if I gave him 1 candy, or them 1 candy, then this is what our thing would go to. So 5, 5, 6, 8, 8, 9. So we have a 6 here because we increased this one by 1. So they are now 6. And they then move to the right of the person to their right because they still have a smaller one. So now we need to increase the median again. 6, 6, 8, 8, 9. And since it didn't grow larger than the one to the right, we can keep it the same. Now we're down to 2 candies, so we'll increase the median to 7. So 2, 2, 4, 5, 6, 7, 8, 8, 9. This person moves to the right because they grew larger than this person, and then this person moved back to the left, and we can give them 1 more candy. And that's our 4th candy, so our highest possible median value is 7. Does that make sense? Because with mean, you can give all 4 candies to one person, and the average will go up. However, with median, it's the middle number, and the middle number changes if it grows larger or smaller than a number that's to the left or right of that. I hope that makes sense. So we're not adding 4 candies to the original median, because if we added 4 candies to the original median right here of 5, that median or that number becomes 9 and it moves all the way over here, but the median still stays 5. So our goal is to not shift, is to create the highest possible middle number. And to do that, you sometimes have to increase the parties to their right so that way the median doesn't pass them. So essentially, see how this number, if it grow, like if sometimes when we add a candy, it adds it to the person on the right and this number stays the same. That's because the median isn't changing when you add 1. So we're trying to keep all of the numbers to the right of the median the same size as the median or larger than the median. Because if it's smaller, then our median is wrong. Yeah, so right now the number to here, I'll do another variant of this. All right, so right now our median is 6. If we increased this one by 1, our median would still be 6 because it grew larger than this one, so we have to move it to the right. So first we're going to increase both of these by 1. So now that's both 7 and we're down to 4 candies. Then we have 3 7s. We can increase them all by 8. And then no matter what we do to the median, all of these numbers are going to be 8. So if we increase the median by 1 to 9, the median is still going to be 8 because the 9 moves down to the end. So we know our median is going to be 8. I'm going to try and find our pocket picker question in the meantime. Wait, I don't know if I have pocket picker on this practice one. Oh, alright, so we'll do SpongeBob and then the pocket picker SpongeBob, because I guess there's 2 different SpongeBob questions. Alright, so this question is asking, let the random variable x be the number of days that SpongeBob needs to be in Stat 107's office hour to do his Project 1, his mosaic. X has a... Yeah, every time I add a candy, sure. So 1, 3, 4, 5, 5, 7, 8. Our median is 5. There's 4 to the left, 4 to the right of the 5. So our median is 5. We have 6 candies. So we're going to increase our median by our current median value by 1. So it's 1, 3, 4, 4. Median is still going to be 5 because it goes, the 6 moves to the right of the 5s. So it's going to be 5, 5, 6, 7, 8. Increase the median again but it moves to the right again. Increase the median a third time, and it's going to stay in the same spot. So now we have 3 6s instead of 3 5s. And then we'll do that again and again, or 3 more times because we did it 3 times. So we did it 3 times. We can do it 3 more times, and then this would be 7 because we can kind of see the pattern. Does that make sense? So the reason I was able to shortcut it is because I could see that if I increase this one by 1, it goes to 7. And then this one goes to 7, and then we have 1 candy left, and then the last one goes to 7. So this one would go to 7, and then this one would go to 7, and then this one would move to 7. Yep, of course. All right, SpongeBob question time. Is this the SpongeBob question we were looking for? All right, so for this question, first things first is we need to find this p of x. So I'm going to remake this table. So we have x and probability of x. So 1 is 1 day, and there's a 0.25. 6 for 6 days is 0.33. 8 is currently blank. 13 is 0.38. And now remember, this column right here needs the total to 1. So we know what this space is. Has to be 1 minus these 3 spaces. So 0.25, 0.33, and 0.38 is 0.96. So we know that this spot has to be 0.04. Now to calculate e of x, I'm going to write this in the very fancy notation, but it's going to be the sum of x times p of x. So what that means is it's going to be 1 times 0.25 plus 6 times 0.33 plus 8 times 0.04 plus 13 times 0.38. So 1 times 0.25, 6 times 0.33 plus 8 times 0.04 plus 13 times 0.38. Now, to calculate that out, 1 times 0.25 plus 6 times 0.23, 0.04 is 7.49. So we expect him to go to office hours 7.49 times. Does this question make sense? This is just kind of a plug and chug question. All right, I'm going to assume that makes sense. Let's see if I can find a pocket picker. All right, so for pocket picker, in this question, we're trying to calculate the amount that Patrick gets in standard deviation of x in dollars. So SpongeBob has 5 coins. You got 3 dimes and 2 quarters. So coins, the value of the coins, and the probability of getting that. So we have 3 or 4 possible combinations. Our first combination is 2 quarters. and the value of 2 quarters is 50 cents. The probability of drawing 2 quarters is 2 over 5 times 1 over 4. Because we're drawing them with our replacement, so he picks a quarter, you get 1, quarter drops down to 1, coins drops down to 4. Okay. Then there's a dime and a quarter, which has a value of 35 cents, which is, the probability of drawing a dime is 3 out of 5. And the probability of drawing a quarter after that is 2 out of 4. And then there's quarter dime, 0.35. That's me 2 out of 5 times 3 out of 4. And then there's 2 dimes. Has a value of 20 cents. 3 out of 5 times 2 out of 4 again. Because there's... Does that make sense how I got all of those numbers right there? All right, and then we know that these probabilities are accurate because 0.3 plus 0.3 plus 0.3 plus 0.1 is the number 1, which adds up to 100%. Now what we have to do is calculate the expected value of these coins. So we have to do, like I just said, the previous question, the sum of the value times p of x. So in this case, it's 0.5 times 0.1 plus 0.35 times 0.3 plus 0.35 times 0.3 plus 0.2 times 0.3. And we get an expected value of 32 cents. Magical, I know. So now we have to calculate the standard deviation. So the way we're going to do that is it's the square root of I'm going to write this in shorthand notation and I'm going to expand it. So it's the square root of x minus x bar squared times p of x. So square root of 0.5 minus 0.35 squared times not 0.32 times 0.1 plus 0.35 minus 0.32 squared times 0.1 plus 0.35 minus 0.32 squared times 0.1, and then, or not 0.1, 0.3. And then plus, and then it's going to keep going down here. This is still under the same radical, I just ran out of room. And it's going to be plus 0.2 minus 0.32 squared times 0.3. Does this make sense? Does this way we're doing it make sense? Is the calculation for the expected value and the calculation, the formula for the standard deviation kind of makes sense a little bit? And so then we get 0.09. I just did the calculation while I was waiting for. Okay. And then that's our answer. So this right here, remember it's all under the square root sign, is equal to 0.09, which is our standard deviation. For variance, if it asks you for the variance, you don't do the square root. You just do that. You get rid of the square root. If it asks you for the e of x, well, you have to calculate that to get the variance and standard deviation anyways. Okay, so Pocket Picker. Everyone good on Pocket Picker now? I should hope so. There's the full thing if you guys wanted to take a screenshot. Halloween costume interval. Do you have the name? Like, see how this one is titled Pocket Picker, and this one is SpongeBob and Stat 107. Do you have like the name of that? Oh wait, no, I found it. Never mind. It is Halloween costume confidence interval. We're good. Yeah, I got it. Wait, I just want to make sure, just right before I start this one, I'm going to scroll away from the work for Pocket Picker. So, last chance to ask any questions. Or not last chance, but, you know, if you have any Pocket Picker questions, throw them in the chat now. And I'm going to get started on this Halloween costume question. Alright, so, when you make a confidence interval, it is going to be your sample mean plus or minus the margin of error. Now, the margin of error is shorthand for this long kind of formula thing. So it's going to be the z of, it's going to be a z-score that corresponds to your confidence level times your standard deviation over your square root of n. Now, so this is what we're looking to find. We are looking to set this equal to, I think it's 0.03 because it's 3%. All right, yeah, I'm pretty sure it's 0.03. So first things first, we gotta figure out what the z of our confidence level is. So the way we do that is figure out what our confidence level is. 80%. So now, to create an 80% confidence interval, we have to do 1 minus 0.8 divided by 2. So that gives us 0.1. So, and then we add that onto our 0.8. So we get 0.9. And then we do norm.ppf of 0.9 to account for the tail. And that is our confidence z-score for an 80% confidence interval. And just to double check, z-score 80%. 1.28, 1.28. So we're just going to use this full one right here because we did calculate that. Let's plug this into our formula. So we get 1.2815515655446004 times, and then now we need our standard deviation and our square root of n. So standard deviation over, and then the square root of n is 200. There's not square root of n. N is 200, so the square root of n is the square root of 200. And we set that equal to our 0.03. Square root of 200 is a weird number, so I'm not going to write it out. But we multiply that times 0.03. So then we get this number is equal to 0.424264067. And then we just divide that by our 1.28155. So this times standard deviation. We're solving this for standard deviation, so it's going to be this over 1.28155165544. And we get our standard deviation is 0.331. I know I kind of just talked and then like showed the numbers, so if you need me to go over it in more detail, let me know. Any questions on this? Because I did just kind of put a lot of work on the paper, so you might have questions on, you know. All right, well, if you don't have any questions on this question, do you have any questions on any of the other questions? Any questions that you've possibly struggled with on this exam? .42. Where did that number come from? Okay, yeah, I did skip that part. This .42 came from taking this .03 and multiplying it by the square root of 200. Yeah, I'll go back to that one. Good question. How do we know when to use .ppf versus .cdf? Okay. So so ppf is essentially like, CDF gives you the area to the left of a point. PPF, you enter in an area, and it gives you the point with that area to the left. So CDF is, if you have a z-score, you plug it into the CDF to get the area to the left. If you have an area to the left, you can, you know, throw in the area to the left here is 0.9, so it outputs a z-score of 1.28. So if I did norm.cdf of the of the 1.28 should output us 0.9, which is the area to the left of that. So it's the inverse of each other. So if you have an area, you use PPF to get the z-score. If you have a z-score, you use CDF to get the area. Okay, FIFA question right here. All right, position 1 was right back. And we know they need a score of 60, so this is going to be conditional. And then we're just going to go ahead and copy and paste this, and then swap out what position it is. So we're doing right wing instead of right back. And then we got to run a 2-sample t-test comparing the weights between those two groups. So it's going to be using this t-test underscore IND. So the t-test underscore IND go to the scipy.stats.t-test that, so that's how we use the function, and then we just have to compare the two wages. So we just filter it to get our positions with greater than or equal to 60 overall, and then we're comparing the wages. That's how I need to use this column, and then we compare the wages of our P1 and our P2 using this function, and then there's the syntax for the function. That makes sense? All right, any other questions? We've got about a half hour left before we're going to wrap it up, but office hours start right after we wrap this up. So any other questions, burning questions? All right, if there's no questions here, I can see if I have a difficult coding question. If there's no questions, I can pick a few more random ones, or I can find the admission rate question, because I know people struggle with that one. Don't think I have it on this test, but I can very easily pull it up. But for this one, you guys know this by now. You gotta have the pd.read CSV. Doesn't have that. This one you're kind of looking at physics C. School X is the higher rate. This one you guys know how to do. You just check to see if admission was accepted, and major was B. That's just a coding question. I'm sure you guys remember the difference between an observational study and a randomized experiment, and you know what all the conditions mean. But this is an observational study because they just kind of looked at the behavior. They didn't run any tests on it. Scared me for a minute. This one, physics B. Well, 90% school X. Yeah. Confounder is, y happens because of the confounder, and x happens because of the confounder. A causal link is x causes something, which causes y. That's the difference between those two. So this one's like neither, because it doesn't really even, it's talking about nuts. Nuts are more expensive. So this is a confounder because, richer people can eat nuts, which probably means if they can afford the expensive nuts, they can afford to go to a doctor. Nuts are high in antioxidants, so you eat nuts, you get more antioxidants, you get a lower heart risk. So there's your causal link. This one, it's, filtering in a data frame. So it's df at df dot subject. You guys have done this a million times. I know y'all can do it. Alright, so only 5 of 16 in group A were female. So what we could do is block the subjects. We want to, divide them into men and women, and then assign them their groups. That way we get an equal number in both. And there's nothing. This is just you checking to see if the admission was accepted. You guys have done that a million times. There was no fake surgery. No group received a fake surgery, so there's no placebo. So it's not C. And then the evaluators were aware, so it was not a double blind, so it's not B. And it's not an observational study because they're doing random stuff. They're, running an experiment and all that stuff. This is just a tracking, no experiment. It's just an observational study. If you divide the numbers by 3, the mean also gets divided by 3, so it's standard deviation of hours of sleep. You just do df at you create a df of freshman. School year freshman, and the standard deviation is df fresh at hours of sleep dot standard deviation. Easy. You guys can do that. We just did this one, and it's just df at school year freshman sorry, what did I do wrong? Oh, capital S. You guys, we've done this. You all can do this. Major that admitted the fewest students. So that is a group by. So group by, and we're grouping by the major. Well, first we have to figure out who was admitted in that. So it's going to be df at df dot admission accepted, and then it's going to be df admitted dot group by major, We're aggregating by the count. And then it's just going to be dot n smallest one and the column of admission. Seriously, guys, there's no bad questions. If you need me to do anything, I'll show you how to do it. Like this one, we're grouping by, and then I just did the n smallest on the same line. You can do that, kind of a life hack. This one we've done already. You just take the df at b's, divide by the df at count. The mean of this one is, 0 plus 2 plus 4 plus 5 plus. And then you divide it by 1, 2, 3, 4, 5, 6, 7. There's how you do your mean. If the first 3 bins have an area of 67%, we know it has to add up to 100%, so we can, nope. Oh, one side is a percentage, so it's 33, but, it'd be 100 minus 67. I didn't realize one of those is a percentage. What is the height of the third bin? So the width is 10. The width is 10. The area is 0.1 or is 12. So that the height is 12 divided by 10. So the height's 1.2. All right. Well, I will give you guys. I'm gonna keep doing these questions. I'll give 3:45. I don't get any more questions. I'm gonna go ahead and end this because I know Angela has to leave at 3:50 and I have to leave at 4. But if you have any questions, get them in the chat. I'll keep answering them until 4. But if not, no questions by 45. I'm gonna go ahead and end it. So if we draw 2 cards at random with replacement, so we draw a card, look at it, put it back. What's the probability that they're both 4s? So the probability of drawing 1 4 is 4 over 52, because there are 4 4s in the deck of cards, 52 total cards. And then the probability of drawing 2 in a row, you square it, you multiply it by 4 over 52 again. That's how you do it. Draw 5 students with replacement. What is the probability that none of them are coffee drinkers? That is 39 over 94. That's probability of 1. 5 of them in a row, you raise it to the 5th power. What is the probability that none of the 2 people share your birthstone? My birthstone is I don't know what it is, but 1 in 12 chance of them having mine, 11 out of 12 of them not having mine, 2 students, so we just square it. Square the probability that one of them doesn't have it because there's 2 of them. Each question has 5 possible answers, so 4 wrong answers. If we guess randomly on each question, what is the probability that we answer all of them wrong? Well, the probability of getting one of them wrong is 4 over 5. The probability of getting all 3 of them wrong is 4 over 5 cubed. You draw 2 cards at random without replacement. What is the probability that both cards are not 3s? Probability of drawing a 3 is not drawing a 3 is 48 out of 52. And then the probability of drawing a second card without putting the first one back, that's not a 3, is 47 over 51. All right, about 5 more minutes or so until the questions, until I'm going to stop answering, or until we're going to end this. So make sure you get your last minute questions in. But I don't think there's too many people in here, so if we only draw from the females, what is the probability we get an ambidextrous person? There are 16 ambidextrous females, women, and 627 total women. So our probability is 16 ambidextrous over 627 women. Is this uniform? 32, 33, 34, 5, 6, 7, 8, 9. There's an equal chance of all of them. If there were like 2 35s, it would not be uniform because you're more likely to get a 35 than any other number. Okay, this one's always complicated. So this one is the tree question. So we have 100 women. 45 of them are pregnant. 55 of them are not. Daily sugar intake. Yeah, sure. I'm going to finish. I'll do this tree one and then the daily sugar intake. Not. So the test is accurate 73% of the time. So it'll correctly label a pregnant woman as pregnant. It'll correctly label 32.85 pregnant women as pregnant. And it will incorrectly label them as not pregnant 12.15 times. And I'm going to do the same thing over here. 55 times 0.73 is 40.15. The way I'm doing this is to get the correct result is if I know they're not pregnant, the correct result is a negative test. So you take the probability that it's correct, multiply it by the number of women in that category, and that'll give you your correct result. And then you can just kind of subtract them off. So there's a 14. All right, and it's asking what is the probability that a randomly selected test is positive? Well, we get 32.85 plus 14.85 is 47.7, and then so it's just 47.7 over 100, 0.477. I went fast on this one. I've done more detailed explanations. If you want me to go back, I'll go back. All right, daily sugar intake. Do you know what section that's in? Oh, random season. I'll do that one too. I think it's going to be down here. This one right here? Alright, cool. So, daily sugar intake. Let X be a random variable representing the amount of daily sugar intake of an American. Okay, so the way we do this is we have to calculate the probability that X bar is greater than 59 and less than 65. So the way we do that is we just find two z-scores. So we'll do our lower z-score, so 59. Remember the formula for z-score is X bar minus mu over standard deviation over root n, which is X bar minus, so it's sample mean minus population mean over standard error. So first, let's calculate our standard error. It's 8 over the square root of 58 to get us 1.05045143. Is that? All right, and then now we just got to do X bar, so 59 minus our population mean, which is given to us up here of 63, over our standard error of 1.05045143. And so that is going to give us 59 minus 63 divided by that. That is going to give us a z-score of negative 3.870886552. And then we'll do the same thing with our 65. So 65 minus 63, divide by that. It's standard error that we calculated. We get 1.90394794327 So we're trying to calculate the probability that negative 3.87 is less than or equal to z, which is less than or equal to 1.903943276. So let's get the area to the left of the first one. So norm.cdf of negative it's a very low number. And then let's get the area to the right, or area to the left of our second number. Why is that not code? And then so the area to the left of that one is 97%. So if we take our 0.97 that we calculated here, that's going to be like this. So that's going to be all of this right here. And then if we take that 5 times 10 to the negative fifth, that's going to be all this data here. So in order to get the desired outcome of what's in the middle right here, we just take this area, the black area, which goes all the way into the purple, and then just subtract off the purple area. So we'll do that by taking the 97 and then subtracting this, the 5 times 10 to the negative fifth, and we get that, which should be our right answer. There's a video on that too if you don't understand. Yeah. Does that make sense? Here's all of the work that I did on that if you need to take a screenshot. This is the black area. This is the purple area. And then the red area is equal to the black area minus the purple area. Alright, does that make sense? Awesome. Yep. All right. So that was gonna be the that was the last question I've received. Nothing else came in after 45. So I will answer 2 questions that I saw that because I haven't answered anything from simulation and distributions. So I'm gonna do 2 or 3 or 1 or 2 of these. I'm gonna do a few of these coding questions. So def random season is a function, so that's how you create a function. And you're just doing a random dot choice, and because it's a list of strings, so you can't do random dot ran int. So you're just only choosing from those 4 choices. And I did something wrong. Oh, I didn't return this. You just gotta return that. And then, alright, do a simulation one. So remember, you do data is equal to the square brackets, and then we're going for 5,000 times, so for I in range 5,000. How are we gonna do it? First, we need to get draw one is a random dot rand int 1 and 15. Draw two is also a random dot rand int between 1 and 15. We gotta do the dictionary, so D is equal to draw one colon draw one comma draw two colon draw two. I know you guys know the syntax, you've done it a bunch. I do just want to finish it one more time. I'm gonna do data dot append D, and then you do pd dot data frame of data. That should be how you make a simulation. So you create a list, you do your for loop, you create your dictionary by creating these variables, append it to your list, and then create a data frame. Alright, so we do have a default this is a function with a default value, so def sum dice, dice is equal to 2, and for sum is equal to 0, for I in range dice, sum is equal to sum plus random dot rand int 1 to 6, because you just want to add a random number between 1 and 6. This is how you roll a die. You add it to your sum, and then when you're done, you just return sum. So that's the dice comes from the parameter that's passed in. If they don't pass in anything, it uses 2. That's what the is equal to 2 for. The sample space is 4 times 20 times 20 because those are the possible different numbers you can roll. This one is pretty easy. You just got to change the thing in the for loop. Okay, I'm gonna answer one more question, and it's gonna be this one, or no, not this one, it's gonna be this one. So we need to calculate the probability of drawing one red and one white. And there's two ways you can do it. You can draw a red and then a white, or a white and then a red. So it's gonna be, that's how we do it. So df dot draw one is less than or equal to 4, because that's a red, and the second draw, df.draw2, is greater than or equal to 11, because that's how you do a white, because if it's more than, or if it's between 11 and 14, it's white. You can't go higher than 14, so if it's greater than 14, or greater than 11, you know it's a white. If it's less than 4, same reason. So that's our first condition. And then our second condition is equal to that. And then our probability is you just take the length of the temporary df we just created and divide it by the length of the df of all successes, or of all outcomes. So this is a df of successes, and df is a df of outcomes. Probability is the number of successes divided by the number of outcomes. Alrighty. Why is that wrong? Oh, I gotta flip this. df.draw2 is less than or equal to 4 when df.draw1 is greater than or equal to 11. So that's how you do that question. Why is this taking so long? iPad session there. Okay, I'm not sure why this is taking so long, but you know. Yeah, there we go. 10 out of 10. All right. So if there's no more immediate questions, which there hasn't been in about 10 minutes, I'm going to go ahead and end this. Exams start tomorrow at 8 a.m. Good luck. This should be up to YouTube immediately after the stream is over.